The Physics of Sound and Music. Doc here to help you study for Exam 3. We're going to go to Downloads and find the Silver Bullet 3. Now, this little tutorial here is somewhat fast paced because we're going to go over the review sheets, a double sided sheet. And there are other videos that spend more time going into detail for the foundational aspects of the course in physics, going chapter by chapter. But here is your review, overall review for the exam that's coming up for Exam 3. Here we have first the filters. And your filters, you think of the resistor and the capacitor. This is your narrow hallway. This is your cafeteria. And if you take a lot of time, in other words, the time being great, that would be T here, being great, that means your frequency is the opposite. Remember your formula, frequency is 1 over T. So if your period T is 2 seconds, then your frequency is 1/2 of a cycle per second. And if your period here is 10 seconds, then your frequency is 1/10 hertz, which is 1/10 of a cycle per second. So remember that relationship, we call that an inverse relationship. So that means if you take your time, the capacitor charges up, you get action here, and that means the T is large, the frequency is low pass. And here, when you have the reverse, the frequency being high, that's when the action is up here, and you get the signals coming out of the top here very, very strongly. Transmission is strong for the high frequencies. They go to a small speaker that specializes in short wavelength, tweet, the tweeter, and here these lower ones go to the speaker that specializes in bass, woof, the woofer. Here is your low pass filter that's oriented for left to right reading, and here is your high pass filter. And by picking different indices here, when you have two together, you get your band pass filter. This gives you the rule that you can pass everything below a certain frequency. In our analogy with parties, say below age 40. And this says pass things above a certain frequency, for example, above age 15, and then you get everyone between, that range from 15 to 40. So that's your bandpass. So what these are here are shorthand notations that if you increase the R, you make the narrow hallway more narrow, or put a lot of tables and chairs and junk so that people can't go through the hallway, get to the cafeteria, then it takes more time. If the cafeteria is bigger, hall to have folks have dinner, then it takes time to get them in there and have their dinner. So either R or C increasing means the time factor increases, the time C, and that means your frequency decreases. And this is a way of looking at the cutoff. So if we are very, very low compared to whatever frequency we come up with, then that passes. If we have a frequency beyond that, for a low pass filter, it doesn't pass. So that is a way to understand the effect of C and R on the cutoff frequency. If R or C increases, that means the time increases for the circuit. That means the characteristic frequency decreases, and that is a measure of your cutoff. So whatever that frequency is, if you're lower than that, you get through for a low pass filter, and if you're higher, you get through for a high pass filter. Here is the ideal low pass filter sketch. Whenever you have graphs in our class, and there's about maybe 10 or so for the entire semester, always know what is on each axis. Here is the frequency, here is the amplitude. You could also say transmission, the amplitude of transmission, what gets through the filter. And you could also have percentage. Sometimes just put percent, 100% for example. And that means here we have low pass because anything to the left here gets through, and here we have high pass, and there's the band pass. Bandwidth is your range that gets in, and your center frequency defines where it is. So you might say 300 hertz with the bandwidth of 200, which means you go either side at 300, 100 to get your 200 hertz. Your resonance filter looks like the resonance graph, where you get a great response if you're somewhere there in the intermediate at the resonance frequency. If you're low, not good. If you're high, not good a response. But here you get the transmission, and that has a parameter, the Q value. If you're tall and narrow, you have a high Q value. If you have a low Q value, you're the opposite, short and wide. You need to know your spectra here, and there's a video from the previous exam that shows you how to memorize these very, very easily. You put them in order of the pictures, looking more, say, away from the sine wave picture, so you should sketch these. It'd be good to do that here in the margin. And these are richer and richer as you go down. So here the first one's one harmonic, the first harmonic, and nothing else. And the last one's all the ones. And then when you come in from below, ramp is next in richest. Second to the most rich here, you chip away and go 1, 1/2, 1/3, 1/4, 1/5. When you get to the ramp, to the square, you just kill the evens. And then to go to the triangle, you square the square. In other words, 1 times 1. 1/3 times 1/3 is 1/9, and 1/5 times 1/5 is 1/25. Here's your rule for harmonics, always true, that the nth harmonic is n times the first one. So F represents the first one. You could put a little subscript there if you want, F sub 1. And if you want the fifth harmonic, then it's 5 times the first harmonic. That's the frequency. Remember that wavelengths work in reverse, because when you increase the frequency, you decrease the wavelength. And the same goes with the frequency and the period. When you increase one of these, the other one decreases. So we go on here to the equalizer, which is a group of active filters, simply bandpass filters, and the amplifier is attached to those so you can control the volume. And they're spaced in this nonlinear fashion where you double as you go, and to make the numbers look good, they tweak them slightly. So 60 times 2 would be 120, but they want 125, so you get 250, 500, 1000, 2000, and 4000. So with the tape on playback, you have his 5K, so the Dolby system boost recording, that's the Dolby recording filter, and on playback, you reduced the higher frequencies. Remember, this is a quick review. There are longer videos that explains these things in more detail. The DBX compounder handles the limit of tape, because tape gets saturated, only can handle 50 decibels, so you divide the decibels by 2, lay that down on the tape, and then multiply by 2 with the electronics when you expand and play it back. And that makes the noise which you hear hiss, the hiss noise that you hear on playback, it suffers when you expand. It pushes that down. Bob Moog, the synthesizer, VC stands for voltage controlled, or voltage controlled oscillator, voltage controlled filter, an amplifier. And here the convention that we're using, we have a circle for a generator, a source of sound, audio sound. We have a triangle that modifies, and then we have a rectangle, which is a controller, a control voltage. The audio signals go from left to right, and these are above second floor, first floor. All of the control voltages have arrows pointing up. So think of the control voltages with arrows pointing north, and the audio signal with the arrows pointing east. Here you have your 3 main controls of the 3 characteristics of sound, the big 3. You have loudness, you have your pitch, and you have your timbre, which we talked about earlier in our course. Here you have the pitch control. By hitting different keys on the keyboard, you then get different pitches. Voltage comes in, tells the VCO what pitch to hit. Then this one here allows you to filter higher harmonics and shape the timbre. Notice that you have filter tracking, so that if you play higher and higher notes, the filter has to adjust so that you can in a relative way get the same kind of effect. If you want to let the first two harmonics through, then when you go up the scale, increase your frequency, the filter has to adjust so that once again you get the first two harmonics through. Then the VCA controls your amplitude, and this is split second control where you have a plucking sound or say an oboe sound that starts off, it takes a little bit longer. It takes longer to come into play, maybe take half second, while the plucking sound could be a thousandth of a second, and both are less than a second, but they're still quite different, the plucking sound versus the oboe sound. And the ADSR tells this amplifier what to do. There's a house system here that has an overall amplifier and speakers that we all can hear this, but this is the synthesizer here. So the trigger from the keyboard lets you know if a key is pressed or not. So when you press the key down, this kicks in. ADSR shapes the amplitude gets shaped at that point. When you have a key pressed, it stalls on the sustain level. It stops. In other words, that keeps going. So if you hold your finger down for 20 minutes, then you keep hearing the sustain phase. Then when you release the key, the release phase kicks in. The LFO is used for modulation. You have three types of modulation for the big three here. You have amplitude modulation. You stick the LFO in there, and this sums the voltages. You can have more than one input to the VCA, the VCF, and the VCO. And then if you put the LFO in the middle region here into the VCF, that will change the filter characteristics. And if you put it over here, it'll change the pitch characteristics. The pitch will go higher and lower. That's your vibrato in music. And if you do a lot of it, sweep it, big time, then you get a siren. And here, this is timbral modulation. So frequency modulation, timbral modulation, and amplitude modulation, and the musical term for amplitude modulation is the tremolo. So here we have white noise. We could just generate all the frequencies. Do not need any control there. Just simply turn it on, and there it goes, white noise. And low pass gives you red noise, band pass green noise, and high pass blue noise. With an analogy with light, white light consists of all the colors of the spectrum. Your low frequency reds, your middle frequency greens, and your high frequency blues. If you divide the spectrum up into three simple thirds, like they do in multimedia, we do computer, HTML, RGB, the RGB model, and also engineers do that with color television. So we have the audio voltage signals go from left to right there, go east, and a control voltage bottom up. So then we move on to here. It looks like we have attack release. The simple model, the two-part model of sound shaping just has the attack and the release, and you get your standard four sounds: your abrupt, gradual, explosive sound, your staccato sound, tap tap, and your sucking sound has a gradual and an abrupt end, and your swishing sound, or like the ocean, the waves coming in. Attack, decay, sustain, release is your four-part model for sound, very important in the synthesizer. All here are preset, except for the sustain in terms of how long they last. The sustain goes as long as you want to last. There actually is a way to set the sustain a little bit there in terms of how high it is, in other words, how loud it is. But this is saying the time presets. The time presets here are for the attack, the decay, and the release. You control the time frame for the sustain phase by pressing the key down and keeping your finger on the key. So for the sound path in the ear, here it's good to go back and review the other chapter where I have the picture of the ear. This is simply listing the order, the outer ear, here the path where you go to the ear canal, the eardrum, and then you go to your middle ear, the hammer, anvil, and stirrup. Then you go to the inner ear, which is here oval window, scala vestibuli, Reissner membrane, tectorial membrane, hair cells, 20,000 in all, the organ of Corti on the basilar membrane, scala tympani, round window. But the picture will help you put all that together in another video that we have reviewed that chapter. For the place theory of hearing, that simply means that pitch is determined along the basilar membrane, and we hear about 9 octaves. If you start here at the far end, here the eardrums over this side come into 3 little bones, and then you get into the inner ear. You get these first, high pitch, and here you go, 20, double, 40, 80, 60, etc., etc. And you can see each one of these is do, re, mi, fa, sol, la, ti, do, do, re, mi, do. You basically have octave, 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 and you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, doubling at each time, the 2-to-1 ratio. Here we have our magic number line where we do our logarithms, and this is very, very important, understanding the two aspects of the ear. The compression of the numbers on the line follow this kind of a pattern where when you make a step, you multiply instead of adding. That's how the ear can hear so many frequencies in a short distance. This distance here, when you unwind the cochlea, 3.5 centimeters, each octave being 3.5 millimeters. And here, this idea of compressing the numbers also exists for the loudness so that we can hear the pin drop and we can hear the roar of the orchestra, and our eardrum can handle that wide range. So here we're looking at, there's your 3.5 centimeters for 10 octaves and divide by 10 to get each octave, 3.5 millimeters. And here we're going to apply this in both cases, the concept with the decibels. But first, let me just talk about this magic scale again. Every time you take a step, you multiply. So 2, 4, 8, 16, 32, 64, 128. A question that appears on some exams to see if you're thinking about this at the deep level. Say we give you 16, that point, and a point 1, and we leave out these numbers, these three, and have a point in the middle. Folks give the wrong answer if they give 8 or something like that. They take some average, 1 plus 16 divided by 2. That's wrong. What you do here is you have to think what step, when done twice, gets to 16 by multiplication. And the answer is 4. 4 times 1 to get you here, and 4 times 4 to get you to 16. In other words, the number that goes in the middle, when you have 1 on one end and say a number here, 16 on the other, is the square root. What number times itself gives you the 16. So here we have shoe sizes, shoe size 2 there to make those steps. And if you ask the question, how many steps do I have to make to get to 32 with shoe size 2, the answer is 1, 2, 3, 4, 5. And that is doing a log. For example, the log of 64, that means I want to go from 1 to 64 by stepping, shoe size 4, so I can draw a shoe here from 1 to the 4 there. And then if I do another shoe, that's going to take me to 16, 4 times 4, and another shoe, I got 3 steps. So how many steps do I need to take to get to 64 with shoe size 4? The answer is 3. Now we need to translate that into mathematics. That is saying the logarithm of 64 base 4 is equal to 3. In terms of our shoe, it's saying the amount of steps I need to get to 64 with shoe size 4. The answer is 3 steps. Now, when you apply the concepts to decibels, we have 2 rules, and the 2 simple rules are if you double the amount of things you have, these are your things or your thingies, then you add 3. So when you go from 1 to 2 things, you add 3. Doesn't matter where you start. If I start here on 4 and I have 46 decibels, if I then double, I think of this as one group. One group of 4 is one big thingy. And then if I double that to get the 8, I add 3, 49 decibels. So that's the rule for the doubling, and that's the baby step rule, which I call that the baby step. And the mama step rule is when you multiply the thingies by 10, you then add 10 to decibel scale. Always multiply here, think this is multiplication, and think here in the scale I add. Fletcher-Munson curves there. This is giving us the equal perceived loudness curves, and that you should refer to your text and the other review to see the picture. And basically, though, we are very sensitive to high pitches, so around 3,000 hertz, we find things irritating if the sound level doesn't get turned down. So we have masking and perception. Loud tones cover soft tones. That's why a fan or the ocean can help you go to sleep at night, where you hear that nice, covers up other things. Periodicity pitch. This is an important one. The brain puts in the fundamental and those small little speakers I had when I was a kid, and you have these iPods and you had these little headsets. The wavelength for a bass is so large, it's hard for a little thing to do that, but the brain will hear the other harmonics, H2, H3, H4, and figure that H1 should be there. The brain puts it in. So that's the periodicity pitch. And we have for oral harmonics, we have distortion, clipping of a sine wave, then changes the sine wave from a pure sine wave to waveform that then can be analyzed with Fourier analysis, has some spectrum. You get these other harmonics kicking in, and they're called aural harmonics. They're not really there in the original sound, but because the system cannot handle the super loud wave or loud, large amplitude, the amplitudes get clipped. So binaural effects, beats, well, yeah, these are two other things that are in there. This is when you put the sound in each ear, you get the beats taking place. When they don't mix in the air, they actually mix in the brain. In other words, remember your beat formula where you have two frequencies and they're close to each other, like 400 and 402. You get a pulsation at 2 hertz, and that will happen even if there is a separation of the two signals, so that one ear doesn't hear the other, what the other ear is doing. The beating takes place in the brain. And then here for perceiving direction, we have two things that the ear does. One is if things are louder toward the right side, so the right ear gets it, then that's a giveaway that the thing is to the right. And also the phases. Remember your phases, your mountains and crests, and usually here but using that more for low frequencies when the wavelengths are big and the wavelengths are over as many centimeters or meters. Well, we have next here the audiogram, and for the audiogram, here's another graph here. You want to know what's on the axis here. You have your horizontal here. They put this at the top of the numbers. These are the frequencies. Notice that they double, 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 and speech goes from 250 to 4,000 hertz. That's most of speech. And what they do is they check 1 octave lower, 125 hertz, and 1 octave higher, 8 kilohertz. So 8,000 hertz. So when you have some mild hearing loss at the high frequency end, well, they won't even test it. If it's like way up there, you're okay. You can function in society. You can hear folks talking, giving instructions. So this is the range here. So we have left and right ear, two different markings, and this person here has an audiogram that shows hearing loss at the high frequencies. The rock musician, that doesn't protect the ears. Tinnitus, internal sound sensation, or you maybe not be a rock musician but listen to music too loud, you will then suffer hearing loss. So be careful listening to loud music. Internal sound sensation due to neurosensory inner ear hearing loss. Tinnitus. Here we have the model of the vocal system as a closed pipe. And here what we do is we do the approximate size of the closed pipe. And that closed pipe there is 15 centimeters for an adult, about 6 feet tall. And then 4 times 15, the 4L rule for the closed pipe to get your fundamental, is 60 centimeters. And then to find the frequency, we use the velocity formula, which we always should have memorized. We should know this one too here. Anything on this sheet you should really study well. The more you know this sheet, this double-sided sheet, the better off you are in being prepared for this exam. And also, of course, check the old exams and solutions. So here, the frequency is the velocity divided by the wavelength. That's 340 divided by 0.6. That's 0.6 meter. And since that's math is hard to do there, and I only want an estimate anyway, I'm going to make this 350 and a 0.7. Then 7 goes into 35 5 times. And I have 500. How do I know it's 500, not 50 or 5,000? Well, if you divide, what you can do here, if you just divide 7 into here. If you divide 7 into here, you won't get 50. If you divide by 0.7, well, see, 0.7, that's a lot less than 7. So that means you have to go up. You got to go put another 0 on that 50 and get 500. So that's a neat way to check yourself when you're dealing with decimals. 7 into 35 with the 0 on the end there with 350 is 50. 7 goes into 350. 7 goes in there 50 times. And then if you have 0.7, which is in a tenth smaller, then you got to have 500. Sort of like a common sense reasoning there to help you get the decimal straight. The other way I showed you in class is that you can move the decimal place over to 7 to get this as a 7, and move the decimal place over here 1 to get 3,500. 3,500 divided by 7 is 500. So the odd harmonics, that's what you get when you have the closed pipe. And when you're speaking and all kinds of frequencies are there, these regions get enhanced, and they're called formant regions, Formants, formant regions. And on the spectrogram, they'll stand out. They stand out. So we have here some spectrograms to know, and the spectrograms that we should know here are, let's go ahead and get back where we can see this easily, like let's say there, and push this up and push that, like there you go. The spectrograms here, you check the book, it has these all in there for you: barking dog, howling wolf, the square wave, and sine wave, etc., etc. And notice that a sine wave in a spectrogram, since you have frequency versus time, is simply a straight line. It's one pitch. And when you have a sine wave wiggle, that's actually the vibrato going on. Here's that admiring whistle. I can't whistle well, but that's that. Yeah, I can do it. And that's, be careful if you do that. That's not socially acceptable to just go around whistling, folks. So make sure you get permission first. But that's a real nice basic audio, spectrogram here that shows you what a spectrogram can do. And by looking at that, that's one it's easy to read. You slide up, and then you go slide up and come down again. You know, very nice. Because some spectrograms, when you're talking, you can't tell what you're saying, but a whistle you can. So that's a really cool spectrogram to analyze. Then what we have here is some music stuff to know here. Okay, so reviewing this. The La Mer, the blues, and the Stravinsky, and all this cool stuff, and a list of composers and musicians down in here to know, and various folks, pianist Martha Argerich here. And what is this? This is moving by a fifth. A fifth is thought of as do, re, mi, fa, sol, la, la, ti, do. You want to go to do, re, mi, fa, sol. You want to go to the sol for the fifth. And here, as we learn in the class after this material, is that the fifth is 5 half steps, where you go from one note to the very next. You go 1, 2, 3, 4, 7 half steps. Sorry, 7 half steps. 1, 2, 3, 4, 5, 6, 7. A fifth is 7 half steps. So if you go up here 7 half steps and do it again, 1, 2, 3, 4, 5, 6, 7, you're at the second degree of the scale. If I go do, re, mi, fa, sol, la, ti, do, re, see, right? And that's 3 halves is our ratio for a perfect fifth. 3 halves times 3 halves gets you up here, which is 9/4. And guess what? That's double the 9/8, which is your re down here. So you have 1 to 1, 9 to 8. So 9/8 times 2 is 9 to 4. A neat little mathematical relationship. Good luck studying for this exam.